Welcome to this lecture on the fundamentals of biomolecules, specifically focusing on phospholipids and glycolipids. Imagine trying to build a microscopic submarine that can survive in the watery environment of the human body. You would need a special material that keeps the inside separate from the outside, but absolutely refuses to dissolve in water. Today, we will explore the incredible molecules that make this possible and learn how cells recognize each other in the vast metropolis of your body. Let us begin by looking at the structure of phospholipids. Why do these molecules matter? Without them, life as we know it simply could not exist, because our cells would just melt away into the surrounding fluid. A phospholipid is a complex biological molecule characterized by its unique amphipathic nature. This means it has two very different chemical personalities. On one end, it has a water-loving or hydrophilic head containing a phosphate group. On the other end, it has a water-fearing or hydrophobic tail consisting of two long fatty acid chains. These components are held together by a glycerol backbone. Because the tails hate water and the heads love it, they naturally organize themselves when placed in an aqueous environment. Now that we understand their structure, let us see how phospholipids function in the body. Because of their amphipathic nature, these molecules automatically arrange themselves into a double layer, known as a bilayer, when surrounded by water. The hydrophilic heads face outward toward the fluid, while the hydrophobic tails hide inside. This creates a selectively permeable barrier. Think of them as strict bouncers at a nightclub, deciding exactly what gets to enter the cell and what must stay outside. This compartmentalization allows cells to maintain a specific internal environment, which is absolutely crucial for generating energy, transmitting nerve impulses, and protecting delicate DNA from damage. This structural behavior leads us to an important mathematical question. Why do phospholipids form flat bilayers instead of spherical droplets? Scientists use a concept called the critical packing parameter to predict this. The formula is P equals V divided by the product of A0 and LC. Conceptually, this compares the actual volume of the lipid tails to the theoretical volume of a cylinder. P is the dimensionless packing parameter. The variable V stands for the physical volume of the hydrophobic tails. The symbol A0 represents the optimal surface area of the hydrophilic head group. Finally, LC is the maximum extended length of the tail. If the tail volume V decreases, the parameter P becomes smaller, which physically forces the molecules to curve into a sphere instead of lying flat. Before we move on, let us see this formula in action with a concrete example. We want to determine the packing shape of a typical phospholipid found in human cells. We are given the volume of its two fatty acid tails, the optimal head group area, and the maximum tail length. We need to find the packing parameter to see if it forms a flat bilayer. We choose our packing formula and plug in the given values directly. The denominator represents the theoretical cylindrical volume. After multiplying the terms in the denominator and dividing the numerator, we get a final value of approximately 1.01. Because this value is very close to 1, it means the lipid has a nearly perfect cylindrical shape, naturally assembling into a flat, continuous bilayer. Now that we have calculated a standard lipid, let us see what happens when an enzyme cuts off one of the fatty acid tails. This creates a lysophospholipid. We are given that the new tail volume is exactly halved, while the head area and tail length remain unchanged. We want to find the new geometric structure. We use the exact same formula, updating only the numerator with the newly reduced volume. The denominator remains exactly the same as our previous calculation. Dividing the new volume by the cylindrical volume yields a packing parameter of exactly 0.50. Physically, because this value is much less than 1, the molecule now resembles a cone rather than a cylinder. It will curve tightly to form a spherical micelle, which can actually disrupt normal cell membranes. These calculations we just performed can be visualized clearly in this diagram. On the left, you are looking at a standard phospholipid. Notice how the two tails fill out a cylindrical shape, indicated by the shaded box. Because it is cylindrical, these molecules pack side by side to form the flat lipid bilayer shown below it. Now look at the right side. This is the lysophospholipid, with only one tail. The shaded region shows it now forms a conical shape. When you try to pack cones together, they naturally curve, which is why the arrow leads to the spherical micelle structure. This diagram perfectly illustrates how microscopic dimensions dictate the macroscopic behavior of the cell membrane. Having explored the structural bricks of the membrane, we now turn to how cells identify themselves. Imagine walking into a massive office building where everyone wears identical gray suits. You would need ID badges to know who is who. In our bodies, cells look very similar because they are all wrapped in the same phospholipid bilayers. Glycolipids act as these crucial ID badges. A glycolipid is a specialized lipid molecule that contains a carbohydrate, or sugar, attached to it. Unlike standard phospholipids, many glycolipids use a molecule called sphingosine as their base. They anchor their hydrophobic tail deeply into the membrane, while waving their hydrophilic sugar head out into the extracellular space so other cells can read their unique signature. Now that we know what glycolipids are, let us look at why their identification role is so vital. These molecules are absolutely critical for cellular recognition throughout the body. For instance, they are the molecules responsible for determining your human blood type. The different blood types are simply different sugar arrangements on the glycolipids of your red blood cells. Furthermore, they play a vital role in the immune system. They help your white blood cells distinguish between your own healthy cells and dangerous foreign invaders. If our cells lacked these glycolipid name tags, our immune system would be completely blind. This would lead to massive autoimmune attacks or leave us entirely unable to fight off infections. This recognition process relies on physical binding, which brings us to the chemical thermodynamics governing these interactions. We can measure how strongly a receptor, like an antibody or a toxin, binds to a glycolipid using the standard Gibbs free energy equation. The formula is delta G equals R times T times the natural logarithm of Kd. Conceptually, this relates the energy of the system directly to how easily the molecules come apart. Delta G represents the standard Gibbs free energy of binding, measured in joules per mole. R is the universal gas constant. T stands for the absolute temperature of the environment in Kelvin. Finally, Kd is the dissociation constant. A smaller Kd means a tighter bond, which mathematically results in a more negative delta G, indicating a highly favorable and spontaneous binding event. Let us apply this thermodynamic formula to a real and dangerous scenario. The cholera toxin infects human cells by binding tightly to a specific glycolipid called GM1. We are given a normal body temperature of 310 Kelvin and a very small dissociation constant of 1.0 times 10 to the negative 8. We are asked to find the standard Gibbs free energy for this toxic interaction. We choose our formula and substitute the universal gas constant, the temperature, and the dissociation constant. Taking the natural logarithm of such a small fraction yields a large negative number. Multiplying these together gives a final answer of approximately negative 47,474 joules per mole. Physically, this exceptionally large negative value indicates an incredibly strong and spontaneous binding interaction, explaining why the cholera toxin is so devastatingly effective at grabbing onto our cells. Now that we have used the formula to find energy, let us understand how to work backward to find the dissociation constant when the energy is known. This is a standard technique in biochemistry. We are setting out to rearrange our fundamental thermodynamic equation to solve for Kd. We start with our standard equation, delta G equals RT natural log of Kd. Our first mathematical step is to isolate the natural logarithm term on one side. We do this by dividing the Gibbs free energy by the product of the gas constant and the temperature. This algebraic manipulation sets us up to easily plug in known energy values and transition smoothly from energy units back to concentration ratios. Continuing our derivation, we will now apply this rearranged formula to a weak immune interaction. We are given a binding energy of negative 15,000 joules per mole at a room temperature of 298 Kelvin. We substitute these values, along with the gas constant, into the right side of our equation. Dividing the binding energy by the total thermal energy yields an intermediate value of negative 6.05. To completely isolate the dissociation constant, we take the exponential, or anti-logarithm, of both sides. Raising the mathematical constant e to the power of negative 6.05 gives our final proven result of 2.35 times 10 to the negative 3. Intuition tells us that because this Kd is significantly larger than the cholera example, the bond is much weaker, allowing immune cells to briefly scan a cell and quickly move on. The weak immune interaction we just calculated is perfectly visualized in this diagram. Look at the bottom section first. You can see the standard phospholipid bilayer separating the intracellular and extracellular spaces. Embedded within this membrane is the glycolipid. Notice how its hydrophobic lipid tails are firmly anchored deep inside the hydrophobic core of the membrane. Now look at the extracellular space above. The glycolipid projects a complex chain of sugars outward. This is the identification tag. Finally, you can see the immune cell receptor coming down to engage with this specific carbohydrate chain. This diagram beautifully teaches how the physical anchoring of the lipid allows the sugar tag to be presented for crucial cellular communication and immune recognition. We have covered a lot of ground today, so let us summarize the most important ideas. First, we learned that phospholipids are the essential amphipathic building blocks of all cellular membranes, creating a protective barrier. Second, we saw how the critical packing parameter mathematically predicts whether these lipids will form a flat bilayer or a disruptive micelle based on their geometry. Third, we discovered that glycolipids act as the vital identification tags of the cellular world, allowing cells to interact and coordinate immune responses. Finally, we explored how binding thermodynamics dictate exactly how strongly pathogens or immune cells attach to these tags. You now have a solid understanding of these fundamental biomolecules and how they connect to keep our cells functioning.